Hello, class. This will be the third of the recorded lectures for section 5.2, which deals with rational functions. And here we're going to talk about two more concepts of asymptotes. This time it's the horizontal asymptote, and I am going to do one example of an oblique asymptote, which we don't use very often. So vertical and horizontal used all the time. So really, those are the two main asymptotes that we'll deal with, especially in this class. So what do we mean by horizontal asymptote? Well, let me get up our whiteboard here and do some examples for you. So when we talk about vertical asymptote, we talk about an equation of a line that would look like that, and that's the vertical, and that would be, for example, x equals 2. And you could have multiple vertical asymptotes and a rational function that we discussed in the last lecture. But what about a horizontal asymptote? Well, a horizontal asymptote would look, obviously, a horizontal line, and it would be y equals something, say that equals y equals -1. So there's a couple attributes about a horizontal asymptote that's different than a vertical. The first one is that you can only have one of them. So you either have 0 of them or you have one of them. And what it does is it kind of splits the whole graph in a up and down style direction, where there could be a line above the horizontal asymptote and then a line below the horizontal asymptote. And so what we're going to do in this lecture here is explain to you how to calculate it. And the strategy is for the calculation is very similar to that idea of end behavior, or the leading term test. Remember, we talked about that in section 5.1 on polynomials. And so the idea is that you want to take this idea of a limit again as x approaches positive infinity. And sometimes you'll see it indicated this way. But all that means is that we want to take the value of x to the biggest value that you can imagine in the positive direction. And so how do we do that? Well, just like we do on the end behavior and leading term test. This idea that the term that has the highest degree will dominate the limit as x gets really big in the positive direction. But now we have to worry about both the numerator and the denominator. So what do we mean by that? Well, let's go over a couple examples. Remember, we did this one, right? We did that one for vertical and domains and intercepts. So here's the horizontal. So the first question you ask yourself, what is the highest degree of both the numerator and denominator? Well, they're both 1. And so then what is the leading term for the numerator? And that would be x. So you put that on top. And what's the leading term for the denominator? That's also x. So you put it on the bottom. And so what's very interesting now is that if we take the limit as x goes to infinity, again, we could do the same thing we did before. You could plug in infinities. This is the engineering way of doing it. And then you could cancel it like it's a real number, even though it's not. I know mathematicians would cringe, but this works every time. And this will help you to calculate limits in calculus as well. So these two cancel, and what do you get? 1 over 1, and that would be 1. So in this case, the horizontal asymptote would be y equals 1. Let's do a few more. Say like you had this crazy one. Say like we had 3x minus 5, and we had 2x minus 1. So you ask yourself, leading term in the numerator, that would be 3x, right? And then leading term in the denominator, that would be 2x. And the limit as x goes to infinity would be 3 over infinity and 2 over infinity. The infinities cancel. You get 3 halves. So again, as a horizontal one, it would be 3 over 2. If we change this to a minus, for example, just bring the minus with you, and you would see that it would end up being minus 3 over 2. So these are a couple examples of when the numerator and the denominator have the same degree. If that occurs, you will always get a value, and you will always get a horizontal asymptote. So what happens if you had something like this? X minus 6, and we did this one before, right? We had x plus 3, x minus 6. So there's a couple ways to do this. First of all, you would cancel these out, right? So that's really important. So you would get 1 over x plus 3. And so what happens here? Well, the leading term in the numerator is the number 1 now, right? And the leading term in the denominator would be x. So when you do this limit, what ends up happening? You would have 1 over infinity. And the way this works, and you have to think about this a little bit, is that if you put a really, 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 really big positive number, right, and you divide it into the number, any number, the value is going to approach x equals 0. So whenever you have more infinities in the numerator than you do in the denominator, the answer is always 0. And the best way to think about that is to get out your calculator and plug in 1 divided by 1,000, and then 1 divided by 1,000,000, and then 1 divided by 1,000,000,000. It's kind of boring, but if you think about it, you'll see that the number is going to get smaller and smaller and smaller, and it's going to get closer and closer and closer to 0. So this would be y equals 0. And that would be the x-axis here, right? That is y equals 0. So y equals 0 occurs quite a bit. And so that would probably be one of the more common. For example, if you had this, x squared plus 2x plus 1. And then you had, say, 3x cubed plus 1. So, excuse me, the leading term in the numerator is x squared. Leading term in the denominator is 3x cubed. And so as the limit as x goes to infinity, you plug in your infinities, you have 2 on the top. And how many do we have on the bottom? We have 3 on the bottom, right? So when you cancel these 3, it'll cancel these 2, and you have 1 left. So it would look like 1 over 3 over infinity. And again, more infinities on the bottom. This goes to 0, and you have y equals 0, or the x-axis again. Okay, so the last of the possibilities is that you have no horizontal asymptotes. And this would be an example of that. Say like you had 2x squared plus 3x minus 5 on the top, and x plus 2 on the bottom. So in this case, leading term in the numerator, 2x squared, leading term in the denominator is x. And as the limit as x goes to infinity, plug in infinities, see what you get. So this will cancel with 1. And now what do we have on top? 2 times infinity. And we have just 1 on the bottom. So when there's more infinities on the top, it just blows up, right? In the sense that as x goes to infinity, y is going to infinity, right? Like we did in the leading term test. And when this happens, there is no horizontal. I messed up. And so that's a good summary of the horizontal asymptotes. And so there is one other asymptote, and I'm going to use this as the example to show you. It happens on occasion. We're not going to focus on it much in this class, but it's good to introduce. So say like we take this same, and we just calculated the no horizontal asymptote. But and the only time you can get what's called an oblique asymptote, it's called oblique asymptote, which is again equation of a line, is when the degree of the numerator, it's not a good end, the degree of the numerator is 1 higher than the degree of the denominator. So in this case, the degree of the numerator is 2, the degree of the denominator is 1. So here we actually do have an oblique asymptote. And so how do you calculate that? It's a little bit tedious, but let me show you how to do it. And you have to use this idea of division. So the idea is that you take the denominator and divide it into the numerator. And we're going to be doing this again, section 5.4, 5.5, 5.5 maybe. So this is a good kind of practice, but how do we do that? Well, one way to do that is to do long division. Remember how you used to do long division? And before we do that, let me just do a quick long division for you, right? Remember if we had like 123 and we wanted to divide 5 into it. So 5 goes into 1 0 times. You usually don't put a 0 up there, right? But you see that would be a 0. So 5 goes into 12 2 times, put a 2 up there. 2 times 10, or 2 times 5 is 10. And remember, what do? You subtract, right? So it'd be minus 10, and you would get 23. How many times 5 go into 23? That would be 4 times 20. And remember, you subtract. And you remember we had this little r of 3. That's what we're going to do again, except now we're going to put x's involved with this as well, and it gets a little bit tricky. So let me go through one example here. And like I said, we're going to beat this up a lot more. I can't remember exactly what section, but coming up quite shortly, probably next week. So the idea is that because we have 2 terms here, we have to do 2 terms in the divisor as well. And so think about it. What you want to do is you want to get rid of the first term. So what do we have to multiply x by to get 2x squared? And that would be 2x. So 2x times x is 2x squared. 2x times 2 is plus 4x. And then you subtract this whole thing, right? And the strategy is the first one is going to cancel. Minus 2x squared plus 2x squared would give you 0. So what would this be? 3x minus 4x would be minus x. And now you bring down the minus 5. And so how do we get rid of the minus x? Well, we want a minus x to cancel with it. So this would be minus 1. So this would be minus x minus 2. And then you subtract it. So you change the signs of both. So this comes to plus x. So that would be 0. And this becomes a plus 2. Minus 5 plus 2 would be plus 3. So our remainder is 3. And so if you take a look at this, you could rewrite it this way. 2x minus 1 with a remainder of, whoops, not plus 3, it would be minus 3, right? Minus 5 plus 2 is minus 3, my bad. So that would be a minus 3 over x plus 2. So like I said, a little bit tricky. Just kind of have to walk through a step-by-step approach. So what does that mean with regards to this calculation? Well, we do know that what's the vertical asymptote? Well, the vertical asymptote would be x plus 2 equals 0, so x would equal minus 2. And our oblique asymptote uses this equation, y equals 2x minus 1. So again, we'll talk about some graphing in more detail next section, but I do want to show you a couple of them and get you previewed for it. So here's an example of this graph. So again, here is calculating the oblique asymptote using long division. And then here is our oblique asymptote. And then you see that our vertical asymptote would be x equals minus 2. So the line, dotted line in red is x equals minus 2. And the dotted line in blue is our oblique asymptote, which basically means you're on an angle. And so it'll have a slope. Not vertical is no slope, right? Undefined slope. And a horizontal is a slope of 0. So what we mean by oblique is it actually has a slope that's not 0 or undefined. So here's a couple points that we want to talk about. So when you calculate asymptotes, you always want to have the simplest form first, right? No common factors. So if you have x minus 6 and x minus 6 in both the numerator and denominator, make sure you cancel it out. So then the vertical asymptotes is after you get to the simplified form, you've all values of x that makes the denominator equal 0. And then the horizontal asymptotes deal with taking the limit, we'll take the limit as x goes to infinity. If you get a number, it'll be y equals that number. If you get more infinities in the denominator than you do in the numerator, it'll be y equals 0, right? It goes to 0. And if you have more infinities in the numerator than you do denominator, that blows up to infinity, and that means no vertical or horizontal asymptotes. And the last one is an oblique asymptote occurs when the numerator is 1 greater than the degree of the denominator. And you can't have, there can only be one horizontal asymptote or one oblique asymptote. They never occur both, right? And so I think that ends the nice summary that we have. Nice summary that we had for the asymptotes. So I think before I end this, what I'd like to do is to go over one big example and kind of do everything that we've learned to date. That would be a good summary. So let's do this one here. So this lecture will be a little bit longer because of this, but I think it's worth doing one. And I'll do a quick sketch with this too. So say like you have f of x equals 2x over x plus 3. So number one, domain. The book likes to use the set format in this case, not my favorite, but I'm going to do what the book does because that's how you have to do your homework in my math lab. So what's the bad value? Minus 3, right? Minus 3 plus 3 here in the denominator gives you 0. Can't divide by 0. So it's all real numbers of x. This crazy line means such that x does not equal minus 3. So what's the vertical asymptote? That occurs when well, first you have to ask the question. Forgot to ask that. Is this in simplest form? And the answer is yes. You can't take x plus 3 and cancel out 2x on the top. So the vertical asymptote would occur when a denominator equals 0. It's good to write that out because it will remind you that an asymptote is an equation of a line. So vertical is x minus 3, and that would be the vertical asymptote. We only have one. So what's the x-intercept? Let's do the y-intercept first. That one's always the easier one. So let's do the easiest one first, y-intercept. So that's when x equals 0. So you plug in, you get 2 over 0 plus 3. And so that would be 0 over 3. And so that would be 0. So actually at the origin, right? So look what happens. What is the y-intercept is the same, and the x-intercepts are the same, right? So when y equals 0, we already did that, right? But if you look at the equation, 2x over x plus 3, right? So the only way to do that is 2x equals 0. So x has to equal 0, and you see they're both the same. So that's the only time that occurs is at the origin, right? Because the x value and y value are both the same, and it's the same point. Because that's the only time where the x and y intercepts are the same. They both have to be 0. And so what's the last one? The horizontal asymptote. And so in this case, the leading term in the numerator, that would be 2x, and the leading term in the denominator, that would be x. And so you see when you plug in the limit as x goes to infinity, it would be 2 times infinity over infinity. So these cancel out, and you get 2. So the value would be y equals 2. So let's kind of show you what this sketch would look like. So we have, let's do it in red here. So we have one point that's actually right here. And so let's do the vertical asymptote. So that's minus 3. So x equals minus 3. Let's do the vertical asymptote, or the asymptotes in green. So there's 1. And then the second asymptote is y equals 2. And so when you do that, you end up like this. So a little preview, the number of lines on a graph is the number of vertical asymptotes plus 1. And so in this case, we have 1 vertical asymptote. So you're going to have 2 lines on this graph. How do you find where the lines are? Well, the bad part is you just have to start plugging in a few numbers. And we're going to do that in the next section. So I'm not going to do that here. But you would see that if you started plugging in numbers, it would look like this. And what's nice is these asymptotes give you kind of where the lines go. And you would see that they would go up here as well. And show you what that a nice looking graph would look like. I do have one up here in the presentation for you. And so you can see up here that you do have a nice little graph up here, and just like we talked about. Again, the x and y intercepts are the same at the origin. The blue line is the horizontal asymptote, and the red line is the vertical asymptote. Cool. So that ends the recorded lectures for section 5.2.